Hi, I'm Professor Stephen Rimmer. I'm Professor of Chemistry here at the University of Bradford, and I'm also the Head of the School in Chemistry and Biosciences. So we sit within one of the leading technological universities in the world. This department dates back to the dawn of the Industrial Revolution. And if you look around this area, you'll see that actually we sit in the middle of one of the UK's largest chemical hubs. We're looking now at many millions of pounds worth of inward investment in this area. We're looking at huge amounts of onshoring as manufacturing industry and research activity comes back, and a lot of it is coming to this area. Within materials chemistry, we're split into three different groups. So a large polymer chemistry group, which I lead as well as leading the department. With nanotechnology, and you'll hear from Dr. Hickey in the next few moments about his work in nanotechnology.
It used to be believed that the properties of materials were based on the material itself. So if I had a big piece of brick or a small piece of brick, the brick looked the same. But we discovered that there is an area of materials when they are small enough, and small here means very small, on the area of thousands or millions of a centimetre, that these materials have individual properties. That is to say that a small piece of material is actually different from a big piece of material. Nanomaterials and nanoscience has proven itself to be one of the most long-lasting recent inventions. In the last 30 years we've made massive strides in this area, and for that reason Bradford has invested heavily in this particular adventure. In a way I feel like an alchemist. Alchemy happens in this lab almost every day. The only difference is that we use size to change the materials, whereas the alchemists try to use different reagents to change it. And so we're not changing necessarily from one material to another, but one set of properties of a material to another set of properties. And that's a fascinating thing to be able to do. Yes, I can feel like an alchemist.
Much of what we do fits at that interface, the important interface between the molecular world and the living world, the biological world, and particularly the medical world.
My name is Maria Katsikogianni. I'm a lecturer in Biomaterials, and I'm very much interested in antimicrobial medical devices. Here in Bradford, we work in collaboration with the engineers, so we work very closely with them from the material processing side of things while we create the new chemistry. Our teaching is research-led, so they have the opportunity as undergraduates to come to the lab. They always work at this interface between, let's say, chemistry and biology. But also, in my case, I bring them over to the engineering a little bit, so they see the processing side of things, how you melt a polymer, how you give it a shape, how you make it into something usable at the end of the day. Our research is driven by a clinical problem, this of medical device-associated infection. And therefore, our aim is to develop strategies to create either what we call non-fouling surfaces that bacteria cannot stick on them and create a biofilm, or antimicrobial surfaces that can release an antimicrobial agent and they prevent bacterial growth.
Everything we do is around that interface of making science work, getting science out there into the real world. The school is composed of around 50 academic staff, and around 2/3 are research active.
I am Dr. Nadeem Javed, and I am working as a lecturer in biomaterials. My main area of research is to develop biocompatible supramolecular materials based on peptides. And these peptidic materials make three-dimensional nanoscaffold hydrogels, and these have application in different areas of drug delivery, tissue regeneration, and crystallization of pharmaceutically important compounds. These scaffolds, they can be a house to regenerate or differentiate stem cells into different kind of applications. We are testing our materials in vivo applications straight away in our school, and then we just link with the engineering facilities and then with the industrial collaborations. And these are making this whole process very quick, that we can bring these technologies to the public, to the end users in very short period of time.
We, maybe around 3 years ago, made a strategic decision to focus on a few areas that we see as important in the 21st century for the development of humankind, etc. One of our aims is to make sure that the graduates, the postgraduates, the postdoctoral fellows we produce fit for that 21st century, the latter part of the 21st century.
The materials we're going to use in the 21st century are, I think, come from the bottom up. We're going to look at the molecular structure of these systems and then build them up into having a macroscopic properties. Can we encode safe degradation of plastics in at a molecular level? Bacterial resistance, can we develop new materials to overcome some of the bacterial resistance, which we know is a major problem in our hospitals? My name is Zach Hughes. I work in the Faculty of Life Sciences here at Bradford, and I basically use computational chemical methods, in particular molecular simulation, to try and understand the physical and chemical processes of systems. A lot of the work I do is looking at the structure of biological systems, particularly the biological systems interacting with man-made synthetic nanomaterials. The structure of these molecules determines their properties, and so if we want to really build up these molecules to applications, we have to know how the structure of those systems is. And trying to do that just using experimental techniques is incredibly complicated. And so simulation allows us to get an idea of the structure of biomolecules, often when they're interacting with synthetic nanomaterials, in a way which complements experimental data. One of the things we're trying to do at Bradford is to really make sure that we give students the hands-on practical experience that they need to work in either the chemical or the biological industries in the 21st century.
In chemistry, we're regularly at least in the top 2 in terms of placing our employment statistics are in the top 2 in the country. And the benefit of being here is that work on the bench, we can take it all the way through to the clinic. So we can do clinical trials. We have in our Faculty of Health, we have a strong nursing group. We can go all the way through to reality.